Well, good morning. Today, the main theme is to go over the algebra of matrices. Basically, what can I do with matrices from an algebraic standpoint, not from a problem-solving standpoint. Solving problems later requires that the algebraic manipulation we do be valid. Now, matrix algebra is a lot like vector algebra, and the things I can do with vectors, most of them are the same things I can do with a matrix. So if you think about vectors, vectors have exactly two things you can do with them in general. You can add them, you can multiply them by a scalar. So we're going to discuss what does that look like in a matrix situation. So I'm going to give you a little definition first of all. So I have a matrix, let's call it A11, A12, dot, 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 A1n, A21, A22, dot, 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 A2n, and then dot, 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 A M1, A M2, dot, 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 A Mn. Okay. This says right here there are exactly M rows, and the second one says there are exactly N columns. So this is an M by N matrix. That's the way we describe it. It's not really complicated. It's a fairly simple notion. Okay. So in general, we would say this is an element of the set of matrices. I used big M, and in subscripts M comma N. Now this is universal notation. Excuse me, Mom, I gotta grab another pen here. I forgot to recharge my pen, so. There we go. So that was dying. So big M, that just means the set of matrices that are of this dimension. That's
Professor,
it. Yes.
do you have a window open across from you?
Oh, hang on.
There's
Yes,
a lot of glare.
How's that?
Thank you.
Is that better?
Yeah. Yeah.
Sorry, I know that the lamp glare is there also. Thank you for that. In vector world, we say vectors are an element of, R2 or R3 or Rn in general. Matrices, because they have two different dimensions, we always indicate this way. So if I had, for example, keep it really simple, I have the matrix 2, -1, 3, 4, 0, 5. This matrix is an element of the set of 2 by 3 matrices. It's real simple. Okay, this is the set of all matrices of this size. Okay, so the first rule of matrix addition, which is what we're going to define first, we say if matrix A and B are elements of this, I'm saying they are the same size. First rule of matrix addition, they have to be the same size, or the addition is not defined. Absolutely critical that we understand that. So when I'm doing this process, if matrix A, we'll write it, I'm going to write it this way: A11 dot dot all the way to A1n dot dot AM1 dot dot AMN. The dots means I'm just continuing the pattern. Matrix B, we'll call it B11 down to BM1, B1n down to BMN. Okay. We often write it this way, and this is really brilliant shorthand notation. We'll write it as one term, matrix Aij. Now this is notation that's introduced. This one symbol is going to represent the entire matrix. And what we do is we'd say that I is between 1 and M. J is between 1 and N. This represents an entire matrix, but it's shorthand notation. Okay, it's shorthand notation. It allows me to describe things actually in a simpler way. And then we do the same thing here. We say this represents the matrix of Bij's, where I is the first, B is the second. Now, with that said, we now can define matrix addition. And it's defined this way. Make sure you guys can see this. A plus B. I have two matrices of the same size. When I add them, I add the corresponding components all the way down the line. We're going to call that Cij. And in fact, I'll make it simple. I'll call C the result of A plus B. And we'll call it Cij, where each Cij is the result of Aij plus Bij. Now, this strange notation is actually quite universal. Again, this is notation out of convenience, not for confusion. I'm going to represent, maybe this is a huge matrix. I'm going to say this is the matrix of Aij's, where I goes from 1 to M. M can be huge. J's go from 1 to N. So there's M times N actual elements in that matrix. When I add two matrices together of the same size, I get one matrix, and the result is every position in that matrix is a result of the sum of the same positions in the other two matrices. So let's do a simple example of this. I mean, this is not conceptually difficult at all. So if I have matrix A, let's say is 2, 4, 0, 3, -1, 8. And matrix B, let's say is -2, 5, 1, 3, -6, 2. Okay, then A plus B. Well, first of all, this is a 2 by 3 matrix. This is a 2 by 3 matrix. So this addition is defined. And the resulting matrix would be -2 plus 2 in the position, 4 plus 5, 1 plus 0. Over here, 3 plus 3, -1 plus -6, 8 plus 2. It's exactly what you think it was supposed to be. Very similar to what happens if we added vectors. So those of you who have had Calc 3 and you understand vector addition is defined pretty much the same way. If two vectors are in the same dimension, then the sum of the two vectors, or I add the corresponding components all the way down the line, so the resulting vector is still in that same dimension. That's huge. Okay, if I take two matrices that are the same size, but they come from the same set of matrices, their result will also come from that set. That's called closure of addition. Okay, and we're familiar with that in other areas. That basically means if I take two elements of a set and add them together, that result is also in that set, since matrix addition is only defined when the matrices are the same size. Right? So that's a really, really simple notion there. Okay, so with that, what about the algebra of matrices versus the algebra of real numbers? Now, real numbers, if I talk about real number addition, okay, we have several properties of real number addition. I'm going to go over some really, really basic stuff that you guys already know, and we want to see how much of it applies to matrices. So, for example, if I was trying to solve the following problem, let's say x plus 3 equals 8. I'm trying to solve this problem algebraically. I'm in a remedial algebra class. Doesn't matter. What allows me to solve the problem? Well, you say, well, the first thing I want to do is I want to get rid of that 3. So I'm going to add a number to both sides of the equation. That's called the addition property of equality. The addition property of equality in simple English says, if I have an equation and I add the same quantity to both sides of the equation, I will preserve the solution. So I could add 10 to both sides of this. I could add 1,000 to both sides. I could have -7 to both sides. I'm going to choose to add something that undoes the 3. So I'm going to choose the additive inverse of 3, which is -3. And as we know, if I took x plus 3 and then I added -3, as long as I add -3 to the right side, that's valid. Now, I want to add these two together. So that means I have to regroup. And because it doesn't matter which side I add on, I have commutativity of real number addition. When I add, I have to regroup. That's associativity of real number addition. When I add the 3 to the -3, I get 0. 0 being the additive identity. And when I add 0 to x, I get just x back again. And funny thing is, all of us could do this in our head in about 1.5 seconds. But if you said, what steps did you do and how do you validate it? There are exactly 5 steps. Yikes. I used the addition property of equality, commutativity of addition, associativity of addition, additive inverse, additive identity. It's not possible to answer this question without all 5 of those playing a role. Now the question is, do matrices have the exact same properties that real numbers do when it comes to addition? Well, it turns out they do. And by the way, this isn't true for all things mathematically, but we know matrices do. And again, for those who've had Calc 3, you know vectors also do. So let's see if we can make sense of this. Is there a matrix out there? Let me start with something really simple. Let me say that matrix A is 2 by 2. I'm going to use something really small. So A11, A12, A21, A22, right? I want A plus B. First of all, I want that to equal matrix A. And we'll call matrix B, B11, B12, B21, B22. I would like matrix A plus B to equal matrix A. Well, based on our definition of matrix addition, matrix A plus B, I know equals A11 plus B11 in that position, A12 plus B12 in that position, A21 plus B21 here, A22 plus B22 here. And I'm asking you to make sure that that just equals this. Well, algebraically, how is this possible? How could this quantity ever equal this quantity? Anybody? How can
All
that
B
be?
values have to be 0.
If all the B's are 0. So B11 equals B12 equals B21 equals B22 equals 0, which would mean my matrix B in this problem was 0, 0, 0, 0. I found a matrix that when I added it to A gave me A. I just found a matrix that that acts like an additive identity. In real number addition, 0 is the additive identity. I found a matrix that has the same property that when I add it to another matrix, nothing changes. And that would be the matrix of zeros. Now, you guys are never going to guess what we call this. We have a really, really clever, really cool name for this guy. Anybody want to guess?
Is it like a trivial matrix or something?
No, it's cooler than that. It's called the zero matrix. So you'd never guess that name. We call it the zero matrix. And sometimes we write it this way. We write a big 0 and then put 2, 2. And the reason I put 2, 2 is how many different zero matrices do you suppose there are? Would there be a 3 by 2 zero matrix and a 2 by 3? Yeah, there's infinitely many because every single shape can have a matrix of zeros. So when we describe the zero matrix to be lazy, we love being lazy. If I put the size of the matrix right here, then I don't have to do this. What if it was a 10 by 10 matrix? That means you're going to write 100 zeros. Yeah, it could be easier to just write it like this. Now, by the way, do not confuse the zero matrix with the number 0. Oh, no, 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 no. Matrices and scalars have nothing to do with each other. Yeah, so a matrix and a scalar are not from the same universe. So we found a matrix that acts like an additive identity. Now, let's do this problem again. Similar problem. But now what I want to do, I started with the same A plus B, but now I want A plus B to be the zero matrix, meaning I want to add A plus B and get this. Well, how could that be? That would only work, but we said this was supposed to be A11 plus B11, and this was supposed to be A12 plus B12, and so on. This could only happen if B11 equaled the negative of A11. If B12 was the negative of A12, B21, whoops, getting ahead of myself here, B21 negative of A21, and finally B22 being the negative of A22. It could only happen if matrix B was the negative of each of these. And negative A22, and we just write that as negative A. So is there a matrix that acts as an additive inverse? Yes, there is. With real numbers, the additive inverse is a number of the opposite sign. So if I take any two numbers and add them together and they're opposite signs, we know we're going to get 0. If I say 8 plus negative 8, or negative 50 plus positive 50, if I take the same value, opposite signs, we add them, we get 0 every time. Is there the same property with matrices? Yes. If I take a matrix where every value has the opposite sign and then I add it, beautiful. So we've got that. Now, what about commutativity and associativity? Will those apply? So here's the question in general now. Because again, I want to know what parts of matrix algebra act like real numbers. Whoops, not equals plus. Well, since this I know was A11 plus B11, A12 plus B12, A21 plus B21, A22 plus B22. By the way, the conclusions I'm making will be true for all sizes. I'm just using really small matrices to save all the writing. These are real numbers. And I know that real number addition is in fact commutative. Because B11 plus A11 plus B11 is equal to B11 plus A11 because real number addition is commutative. That's not even in question. But if I add A plus B, I get this result. Within this result, I can do this, but then this ends up being B plus A, isn't it? So what can we conclude about matrix addition? Anybody? It's a good thing. Matrix addition, it's commutative. Matrix addition is commutative. That's powerful. Matrix addition is also associative for the same reason. If I took a third matrix, the components are real numbers, and because real number addition is commutative and associative, it's going to apply to matrices. Now you say, well, isn't everything commutative? No. No, actually, most things aren't commutative. You see, think simple baby algebra. If I said, A plus B, I know that's B plus A. A minus B, of course, is B minus A. No. A times B is B times A. I know that. A divided by B is B divided by A. No. A raised to the B power is B raised to the A power. No. The eighth root of B is the bth root of A. No. On and on and on. For those who remember your vectors, is cross product commutative? No. No, actually, commutativity is a very, very rare thing to achieve. So when we have it, beautiful. So when I'm doing addition, most everything mathematically when you're doing addition is going to end up being commutative, but not all operations are commutative. That would be a dangerous assumption. So this is kind of nice. This is kind of easy. Well, similar to vectors, there's one other operation that we define with matrices, or I should say that matrices naturally have, and that would be scalar multiplication. Now, scalar multiplication is the idea when I multiply a matrix by a scalar. So if I, again, say, let me call matrix A generically, A11 up to A1n, AM1 to AMN. I'm just going to do the generic. Then for K being a real number, I'm going to use real numbers. Later on, much, much later on in the course, we're going to consider complex numbers and their role, but not for a long time. We want to master real numbers before we delve into that other realm. K being any real number, then K times A is defined to be KA1, KA1N, KM1, KAMN. Or in other words, if matrix B equals K times matrix A, then Bij is K times Aij. The ijth entry of the result is K times the ijth entry of the original matrix. That's what matrix scalar multiplication of matrices means. So keep it simple. I want to talk about 4 times the matrix 2, -1, 3, 6. I have 4 times this matrix. The result is 4 times each entry. That's simple. Okay, there's nothing about that that should trouble us. Very simple, not complicated. Scalar multiplication also, you notice, preserves the size of the matrix. I cannot do an operation, either addition or scalar multiplication, and change the size of the original matrix. That's not going to work. Okay, so with that, that's a fairly simple thing. So let's do a simple arithmetic example. Again, I'm using small matrices just so we can follow along. Let's suppose matrix A is 2, -4, 3, 6, and matrix B is -5, 2, -1, 3. Let's find 4 times A minus 3 times B. This is what is called a linear combination. Okay, I'm taking scalar multiples of my matrices and then I'm combining those results. That's supposed to be a simple process, but sometimes we make it harder than we have to. Because we've defined matrix addition clearly, and now we've defined scalar multiplication, it shouldn't take a lot of algebra. So the simplest way to do this problem and ensure you're going to be correct is, first of all, never do a subtraction. Multiply by the scalar. A lot of folks like to subtract things and then they forget to distribute the thing they're subtracting. So they, it's sort of like if I have polynomial minus another polynomial, we only get the first terms right because we forget to distribute the negative into the rest. Easiest way to do this is, what is 4 times matrix A? That would be 8, -16, 12, 24. Don't subtract, add. Never subtract. Because when you subtract, you're going to make errors that shouldn't occur because we sometimes go too fast and we overlook. Well, what am I adding? -3 times B. So 15, -6, 3, -9. And then my final result, I add the corresponding components. So 23, -22, 15, 15. Okay, pretty simple. Nothing about that should be complicated. So we've clearly defined matrix addition, scalar multiplication. You're saying, this is linear algebra, this is high-level math. Well, we got to start somewhere. You see, we're saying, what can we do? What can we do when we're manipulating matrices? Now, I'm going to give you a definition, and we use this next thing really often. We're going to define something called a transpose. The transpose of a matrix. Okay, so if I have a certain matrix of a particular size, so let's say A is an M by N matrix, and we'll use the same one we've been using, A11 up to A1N, AM1 up to AMN. Great. Then the transpose of this matrix, which we represent as A with a T, kind of where an exponent would be. It's not an exponent. We're just saying A transpose is the matrix A11 to AM1 down to A1M down to A, oops, sorry, I got this backwards. Sorry, that should be N1. Well, actually, you know what? Yeah, I said it right. A1N, and then this would be A. The last position here would still be AMN, but you notice the rows and the columns got kind of wonky. If I had 3 rows and 10 columns, now I have 10 rows and 3 columns. What I did basically, I swapped positions. I'll do that with numbers in a moment. Meaning, let's call this matrix B for lack of a better name. What that means is Bij is equal to A Ji. I swapped the rows and columns. So this guy here ended up here, right? This guy here ended up here. So let's do it with numbers and see what it looks like. So if matrix A was 3, -2, 1, 0, 4, 5, then matrix A transpose, well, first of all, this matrix here is 2 by 3. So matrix A transpose is going to be 3 by 2. It's going to be a different shape. And the rows of A become the columns of A transpose. So 3, -2, 1, 0, 4, 5. So like I said, this is still the upper left, this is still the upper right, but everything else switched places. Interesting. Okay, well, that's a simple thing. We use transposes a lot. Now, I'm going to throw a what if at you. I'm going to throw another definition. Let's suppose matrix A is 3, -2, 1, -2, 5, 6, 1, 6, -7. Right? I'm giving you a square matrix. In this example here, I want everyone to try this. Just do this on your own really quickly. What is a transpose? So take all the rows of A and make them the columns of A transpose and so on. So everyone try this on your own. This should take you like 10 seconds.
Exactly the same thing.
Well, that's crazy. How could it possibly be the exact same thing? Well, in this case, it is. So in my example, my A and A transpose are exactly the same matrix. Now, remember we said on day one, two matrices are equal if they are identical. They're clones of each other. They're the same size. Every corresponding element is the same. A and A transpose are equal. Huh. Who knew? That means that we say matrix A in this example, we say matrix A is, and the word is, symmetric. We like symmetric matrices because they're really nice to work with. If A equals A transpose, A is symmetric. Now, in general, are matrices symmetric? No. No, in fact, in the previous example, I gave you a 2 by 3 matrix and its transpose was 3 by 2. So in general, the transpose of a matrix isn't necessarily even the same size as the matrix. So what would a property be of a symmetric matrix? Tell me a really obvious property for if a matrix is symmetric. Think of versus the previous example. If a matrix is symmetric, it has to be
square.
Has to be square. The number of rows and columns would have to be the same. Otherwise, when I do the transpose, it would be a different shape. So for a matrix to be symmetric, it would first have to be square. That does not mean that all square matrices are symmetric. No, it means all symmetric matrices are square. And that's really important. And symmetric matrices, we're going to use them throughout the course, are really, really nice. They're really, really practical things. So with that, we've got addition, we've got scalar multiplication. Life is good. There's just nothing about that that's difficult. So now what we want to do is define matrix multiplication. Now, with vectors, and again, I go back to vectors because of the similarities. With vectors, we know there's vector addition. We know there's scalar multiplication. So we also had to invent vector operations. The operations we invent are dot product and cross product. And then we have to define them after we invent them and then show all of their properties. Dot product isn't an automatic thing with vectors. We defined it. We made it up, in other words. But there's a consistency and there's a huge importance to dot product. Cross product, we made up and said, okay, here's what we're going to define cross product to be. Vector addition is the only natural operation, and scalar multiplication. Same thing with matrices. There is no preset, okay, here's how you multiply matrices. We could multiply matrices any way we want, really. If I said, here's two matrices, here's how I want you to do the multiplication. I could invent something, and as long as it's internally consistent, we'd call that multiplication. But that's not exactly how we're going to do it. So I'm going to define things first. Okay, let me define matrix A to be the following. Well, actually, let me do it simpler than that. I'm going to actually do it like this. And I'm going to define matrix B. Okay. A is what is called a row matrix. B is what is called a column matrix. A has only one row. So technically, my matrix A is 1 by n. My matrix B is n by 1. This is kind of boring, but we have to start somewhere. So I'm going to define the following. Now, I haven't been using it so far, but many of you are familiar with this symbol. The 3-bar symbol does not mean equals. It means is defined as. Whenever you give a definition in mathematics, you'd say, here's how we're defining the following thing. So we just defined addition and scalar multiplication. We're now about to define multiplication. When you define something, you can't question it. You're saying that's the definition. When you go to the dictionary and you look up a word, you don't say, well, why is that the definition? Why can't it be this? You say, no, this is the way we're defining it. We've used this before. For example, what's the square root of -1? Can you calculate that? No, it's defined to be I. That's the definition of the square root of -1. But then if I said, what's the square root of -4? You can say, well, that's root 4 times root -1, which is equal to 2i based on the definition. This is not a definition. This is a result of the definition. When we're doing trigonometry, we define the x and y coordinates on the unit circle as being the cosine of theta and the sine of theta. And then after that definition, we can build all of our trig. So we're going to define A times B. A times B is a 1 by 1 matrix. A11, B11 plus, A12, B12 plus, all the way to A1n, Bn1. This is a single scalar, okay? This is one number. I took this product plus, all the way down the line. I got a 1 by 1 matrix, okay? So when I take a row matrix and I multiply it by a column matrix, I get an individual value inside a matrix. Now that's kind of boring, but this is the way we do things. So we also define it this way. It's the matrix of the sum A, now notice it, A1I, BI1, I going from 1. I'm sorry, you know what, I got this back. That should be, sorry, that should be 2, 1, not 1, 2. Oh, you know what? Let me try that again. I just realized I didn't put 2 subscripts on these. I only put 1. Let me try that again. I'm getting ahead of myself. Sorry. A and B. All right. So this is defined to be the sum of the AI's BI's. This is very artificial. This is 1 row, 1 column. We don't usually do that with matrix multiplication. We usually have bigger things, but we have to start in one position. So we do this product all the way down the line, and then we add them up as we go. Now, do you ever do anything like that mathematically? Where you multiply and then you add, and you multiply, then you add. Can anybody think of anything else that we define that has that exact same process?
The dot product.
It looks a lot like dot product with vectors, doesn't it? It's because isn't that what we do with dot product with vectors? Is that we multiply corresponding components and we add them to the next and so on. Oh, so matrix multiplication has some serious similarities. It isn't dot product, but there are huge similarities. So now the question is, let's take 2 matrices that are not just a row and just a column. So now we can define everything else. So let me take matrix A. And we're going to say matrix A is M by N, and matrix B is N by P. They are not the same size necessarily. Now, I mean, I could choose, you know, M, N, and P to all be the same number. No. M by N, N by P, the only thing that matters is that that's the same number. So this is the matrix of AIJs, okay? That's one way to look at it. But this can't be the matrix of AIJ or BIJs, so we'll call this the matrix of BJKs. I clearly is going to go from 1 to M. Oops. J is going to go from 1 to N. And by the way, same J. And then K is going to go from 1 to P. So we will define matrix C to be the product of matrices A and B. This is one of the reasons I love this notation. Then in the resulting matrix, okay, we're going to call it the CIK entry is going to be the sum, okay, and I need a new letter. Let's see, what letter shall we use? Running out of letters, so I'll call it T for a second, okay. I have matrix, well, no, actually, I'll leave it as J, sorry. AIJ, BJK, J is running from 1 to N. Now, I know this is totally confusing when you're first looking at it, so I'm going to do it to make it clear. The only thing that matters when I multiply matrices is this is row, column, row, column. The number of columns of the first matrix has to match the number of rows of the second matrix. That's an absolute. That's the only way we define matrix multiplication. Then when I multiply those matrices, my new matrix is going to be M by P as a result. And what's going to happen is I'm going to take a row of one matrix and multiply it by a column of the second matrix, in much the same way I defined it a moment ago. You notice in this case here, the J's are the only thing changing. Okay, so this is AI1 times B1K, AI2 plus times B2K, AI3, B3K, all the way up to the end. Okay, this is the formal definition of matrix multiplication right there. Now let's do some examples, because that looks very abstract. It's exactly what we do 100% of the time. Yes.
I just want to ask, is there anything above the JK in the definition? I can't see it.
So
The
here,
glare from your ceiling light is like perfectly
no,
blinding.
this is no, but it's just C.
Okay, cool.
C.
Yeah, I couldn't see the C.
I apologize, guys. The glare, I don't see the same glare you guys do. I just am aware of it. Like right now, I'm looking at my screen, and the glare kind of goes in and out depending how long I stare. That could be my eyes too.
Is it CJI or CIK?
I'm sorry, CIK.
Thank you.
It's the outer ones. So I'm going to do it. That definition, by the way, is absolute. It's clear, it's perfect, it's flawless, and it's really confusing because that's not what a matrix looks like. You see a matrix with numbers. You don't see I's and J's and K's. So when we actually do it, make it really simple. Let's say I have matrix A is, I'll keep this relatively simple. So 3, -1, 2, 1, 4, 0. And matrix B, now this is 2 by 3. So matrix B must be 3 by something. So I'll make matrix B, how about 3 by 4? All right, -1, 5, 2, 1. 6, -3, 0, 4, -2, 2, 1, 3. Now, I want you to notice this is 2 by 3 This is 3 by 4. So A times B exists. How about B times A? Is B times A defined? Can I multiply B times A?
No.
No, I can't. Ooh, so not only is matrix multiplication not commutative, in fact, more often than not, if you can multiply in one direction, you can't even multiply in the other direction because the dimensions aren't compatible. Oh, remember the rows and columns have to line up. So matrix multiplication in general is not commutative. Yes, you could always find examples where it is, but in general, A times B not only is not equal to B times A, if A times B exists, most of the time B times A won't even exist. Forget that I don't get the same numbers. I can't physically perform that. So I want to do, let's see, I'll do it down here. I want to do A times B. Now I'm going to show you a really simple way to do this so you always get it right. Because this is a very simple process. It's arithmetic. We don't want to make mistakes on arithmetic, but we got to do things in the right order. So I have a 2 by 3, I have a 3 by 4. My result, because these numbers matched, my result is going to be 2 by 4. That's the first thing you notice. 2 by 3, 3 by 4, my result is 2 by 4. But how do I do it? Here's what I like to do when I'm first showing people, because this is exactly the way I do it. I'm taking the rows of A and they're being multiplied by the columns of B. So I literally am going to circle that row. I'm going to circle that row. I'm going to circle the individual columns to remind myself of what it is I'm going to perform. Now, remember how I defined the multiplication of one row by one column? The 1-1 entry of the resulting matrix is the first row of this matrix multiplied by the first column of this matrix. That's the result. So I'm going to go -3 plus -6 plus -4. I believe that's -13. Okay. The 1-2 entry of this matrix would be the first row times the second column. So I'm going to do the same thing. 3 times 5, so I have 15 plus 3 plus 4. I believe that would be 22. The first row, third column entry would be the first row times the third column. So 6 plus 0 plus 2. And then finally, the first row, fourth column entry would be the first row times the fourth column. So 3 plus 4 plus 6, 13. Now I'm done with row 1 of my resulting matrix. Now I'm going to take the second row of A and multiply it by the first column of B, and that will be the second row, first column entry of the result. So -1 plus 24 plus 0, that'd be 23. And in this position, second row, second column, 5 plus -12 plus 0. Here, second row, third column, 2 plus 0 plus 0. And finally, 1 plus 16 plus 0. That's how you perform matrix multiplication. Just don't go too fast. So the only thing you have to be aware of when you're asked to multiply two matrices are the dimensions compatible. Okay, so the number of columns of the first matrix must match the number of rows of the second. So when I'm performing, I have the exact same number in each to actually do the performance. When I switch the order of multiplication, those two usually aren't going to work. And here's why matrix multiplication in general, because if I'm defining the way we did before, I said I think I used CIK. The CIK entry we said was the sum, okay, from J equaling 1 to N of Aij, Bji. All right? That's what we just did. We took whatever row we were on and whatever column we wanted. So let's say I wanted this guy. That was the second row. That was the third column. So I took the entire second row So every time I would always use the 2, so it'd be 2, 1, 2, 2, 2, 3, 2, 4, and so on. Problem is, if I said, what about the sum? Let's now go ahead and switch it. Let's say I want that particular one here. So now I want B, J, I, A, I, J.
Professor,
Oh, I'm sorry. Did I lose something? Sorry, that should be K. Thank you. Let me try that again. So if I said, well, can I do this and then have those guys? Hold on one second. Hold on, I need to pause this just for one brief moment. Basically, when I reverse the order, this was row column. I can't go column row and expect that I'll get the same result because it's not the same set of numbers being multiplied. So even if the multiplication is defined, I'm not multiplying the same numbers. That's why matrix multiplication is not commutative. Remember, for something to be true, it has to always be true. So you don't have to prove matrix multiplication is not commutative. Can it ever be commutative? Yeah, there are situations. For example, if I had 2 square matrices, then when I reverse the order, I'll get the same size. So first of all, for matrix multiplication to be commutative ever, both matrices would have to be the same size and square. Otherwise, my results won't be the same size. So what if one of my matrices is the 0 matrix? And they're square. Well, yeah, then I'm going to get the 0 matrix either direction. There are exceptions, but in general, we say it's not commutative because you cannot always get the same result. All right, so we've got matrix multiplication, and it's not a complicated thing to do. Matrix multiplication is fairly simple. It's just a simple algorithm. Now, going back to the algebra of matrices for a moment, when we talked about real number addition, okay, think real numbers for a moment. I want to undo, I have 3x equals 8. And we did it with addition a little while ago. So what are the rules for multiplication? Well, similar. If I multiply both sides of an equation by the same non-zero value, I will preserve the equality. So I can multiply both sides by 1,000. I can multiply both sides by 1/2. We will choose the multiplicative inverse, which is the reciprocal of the coefficient. So we'd multiply both sides. We'd want to multiply both sides by 1/3. But it doesn't matter which side I multiply 1/3 on because that's commutativity. So I will rearrange and I will regroup. That's commutativity, that's associativity. I will get the multiplicative identity because I'm using the multiplicative inverse, and when I multiply by the multiplicative identity, I get the x. So that's why all the way down the line, and just like the addition example we did, we have to use the multiplication property of equality, commutativity, associativity, identity inverse. Yikes. Now, throw a what if at you. Let me just throw a what if. Would the following statement, I'm going to write it like this. If this was real number multiplication, we'd say multiply both sides by the reciprocal. Is this a legal move if I wrote it? A to the negative first, AX equals A to the negative first, B. Would that be legal? If I wrote it like that, is that legal, everyone? Everybody good? Yeah, you don't usually write things this way. And when you multiply A to the negative first by A, we know we get 1. And when I would do 1 times X, all right, I know I get that. Now, obviously, I would write that as a quotient if these were real numbers. If they were real numbers, we know that's absolutely correct. What if I said A, X, and B are not numbers? What if I said A, X, and B are matrices? Then is it possible that I could do this with matrices? Yes. This would no longer represent reciprocal. It would represent inverse. You go, aren't they the same things? No. Of the infinitely many mathematical operations that can be performed, reciprocal and inverse are only the same if you're talking about multiplying by real numbers. See, Reciprocal is not the inverse of addition, exponentiation, trig functions, logs, exponentials. No. Inverse and reciprocal have absolutely nothing to do with each other in general. Reciprocal is only the inverse of multiplication, not the inverse of any other operation. But when I put a -1 in that position, we know, think functions. When we put a -1 there, we mean inverse function. So is it possible I can undo a matrix multiplication with another matrix? Yes. And that matrix would be called the inverse matrix. So I'm going to set up the criteria that allows us to do something like this. It's kind of crazy. So first thing I'm going to do is I'm going to redefine something very, very important. Now, we could have done this on day one, but we're going to do it today because we would like to know in general if it's possible to solve problems using an inverse. So the first thing I want to do, I want to set up a system of equations. I'm going to write it like this. A11x1 plus A12x2 plus ... plus A1nxn equals B1. That's my first equation. Okay, the A's just represent coefficients. The X's obviously are unknowns. Then the next equation, A21x1 plus A22x2, A2nxn equals B2. Now you see where this is going, hopefully. And now I have a M1x1 plus a M2x2 all the way to a Mnxn equals Bm. I right now have M equations, I have N unknowns. We can write this system of equations now as a matrix product. And by the way, that's exactly how we're going to want to do this pretty much forevermore. What would the matrix product be? Well, I'll write it down. First of all, I'm going to write down the coefficient matrix. Because if you were going to solve this using a matrix, you'd want to do it like this. We'll call that big matrix A. Now I want to have what's called a column matrix, but my column matrix will be the variables, x1, x2, all the way down to xn. Now notice A is M by N. We're going to call this matrix X, and we're going to put a little vector hat on it. This is N by 1. And this whole thing is going to equal B1, B2 down to Bm. Okay, and we're going to call that guy, boom. Now, one of the first rules that we're going to learn, we don't know this before, and some of you may have been aware of this. A column matrix and a vector are absolutely identical mathematically. It's a context thing. Sometimes it's convenient expressing a vector as a column matrix. Sometimes it's easier to express it as a vector. But a column matrix and a vector are identical because they have the exact same properties and the multiplication works the exact same way. So this column matrix here is equivalent to vector x1, x2, ... xn. This and this are equivalent animals, and we're going to be showing this throughout the course. So representing a vector solution as a column matrix is convenient if I'm doing matrix multiplication. Okay, our goal in this problem obviously is to find matrix X, which is a column matrix or a vector. That's our goal in the problem. So the first thing we do is we take any system of equations and we consider it as a matrix product. And you say, well, how is this a matrix product? Well, based on my matrix multiplication, don't I go A11x1 plus A12x2 plus all the way down to A1nx1, and then that result would be the first position here. But that's exactly what the first equation says. Then when I do it again, boom, 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 I get this value, but that's exactly what the second equation says. So when I perform this matrix multiplication and get this, these match the equations exactly. That's why it's exactly the same thing. But if I consider my system as a matrix multiplication, then I might be able to solve my system by finding the inverse of the matrix. Now, we're going to talk about finding inverses. Today, we're going to go easy. the big beefy problems we're going to look at next day. Now, the first rule about finding the inverse of a matrix. The inverse of a matrix only exists if the matrix is square. Okay, you cannot find the inverse of a non-square matrix, but there's still things we can do. So a matrix has to be square. So for me to solve this system and get a unique solution, M and N would have to be equal. Okay, in general, they don't have to be equal, but for me to solve this and get a unique solution, they would be. Okay, so I'm going to go over some really simple algebra. You're going to like this. We're going to discuss how to find the inverse of a 2x2 matrix today. Next day, we're going to do n by n in general. We got to start somewhere. Okay. Let's see where we are here. Okay, we're still good on time. So here's what I want to do. Let's consider I have matrix A. And we're going to make it really simple. I'm going to go A, B, C, D. We want to find a matrix, we'll call it A inverse, so that when I multiply them, I get a particular type of matrix. So now I'm going to define something. I is called the identity matrix. If it's 2x2, it looks like this, and I call that I2. If it's 3x3, it looks like this. I call that I3. So in general, we write it this way. We become really generic. IN I love this notation. Oops, that's supposed to be a 1. First of all, the identity matrix is a square matrix. Okay, it's a square matrix that has 1s along the main diagonal, 0s everywhere else. Sometimes it's illustrated like this. That big 0 means everything in the upper triangle is a 0. That means everything in the lower triangle is a 0. That means everything along the main diagonal is a 1. That's kind of a convenient way of writing it, but it's a little bit abstract. So the other way we represent an identity matrix is as follows. We say that in the identity matrix, Aij equals 1 if I equals j, and Aij equals 0 if I is not equal to j. I equaling j means I'm on the main diagonal. It means I'm the 1, 1, the 2, 2, the 3, 3, and so on. So everything that is not on the main diagonal is a 0. Everything on the main diagonal is a 1. This is a more formal way of writing an identity matrix. So why an identity? Why do I care? Because the identity matrix acts as the multiplicative identity for matrices. It acts like the number 1 does in real number multiplication. So let me do a really simple example. Okay, I'm going to do a really simple example before we start our process, because there is a goal in mind. Let's say matrix, I'll use a different, matrix B. Let's say matrix B, -1, 2, 3, 4, -6, 2. Okay, this is a 2x3 matrix. I want to perform the following 2 multiplications. I want to find BI and IB. I want to do both of these. So I want to do BI. Let's do that one first. Now, this is a 2x3 matrix. So what must the shape of the identity matrix be? Anybody want to try that one? What does my identity matrix have to be? What shape? I know it's square, but what dimensions, I should say?
3x3.
Has to be 3x3. Beautiful. Because otherwise the matrix multiplication would not be defined. So I'm going to write it down, 3. So what do we get when we multiply? We get this and 0, 0. Okay. Then on the next row, and now, excuse me, the next column, we get 0 plus 2 plus 0. And then here we get 0 plus 0 plus 3. Then here we get 4 plus 0 plus 0. 0 plus -6 plus 0. And then 0 plus 0 plus 2. Oh, that's exactly B, isn't it? When I multiplied on the right by the identity matrix, I got exactly B. Okay, now I want to do this multiplication. I want to do the identity times B. Now what's the shape of my identity matrix that I have to use? Is it 3x3?
2x2.
It's got to be 2x2, for the same reasons before, the rows and columns have to be compatible. So this I is clearly going to be I2. I didn't tell you that. We discovered that kind of by doing it. When I perform this, I've got -1 plus 0, 2 plus 0, 3 plus 0. I think you see where this is going. 0 plus 4, 0 plus -6, 0 plus 2. Whenever you multiply a matrix by the appropriate identity matrix, you get the same matrix back. Absolute across the board, unchanging. It has to be compatible. So I can do this, but you notice these aren't the same I's, but in both cases, I got the matrix P back. Very cool process. So here's our goal in finding an inverse of A, if it exists. Our goal is to perform matrix operations, and I'm going to show you how this works. Okay, not every matrix has an inverse. Here's the rules for having an inverse. So first of all, you have to be square. You have to be square because A times A inverse has to equal A inverse times A, and you have to get back the identity matrix. That's the rule. If A inverse exists, then A times A inverse equals A inverse times A equals the identity matrix. That's an absolute mathematical law. If it exists, now there's no guarantee that it exists, but firstly, A would have to be square because otherwise your dimensions won't work. If A is not square, A inverse doesn't exist, and the matrix multiplication would not be commutative. So A inverse equals A inverse A equals the identity matrix if it exists. How do I know when it exists? There's a whole set of things we call the equivalent conditions. Okay, think a system of equations. Is there any guarantee that system of equations has a unique solution? Actually, there is. If I have a system of equations and now I'm writing it in the form AX equals B, like I just showed you a moment ago, that system has a unique solution if A inverse exists. When will A inverse exist? When we did row operations, if you remember, if I could make the left side of my coefficient matrix look like the identity matrix, we called that, remember, Jordan canonical form. If the left side looks like the identity matrix, then the right column was the actual answers. So here's an easy way to think about it. If your coefficient matrix is row equivalent to the identity matrix, meaning I can do legal row operations and eventually get the identity matrix. That's not an automatic. If I can do that, then there's a unique solution. It also means that there is an inverse. So I'm going to do row operations. So here's the way I want you to think about it. Here's my extremes. I have matrix A, I have the identity matrix, I have A inverse. If I can do row operations on A to get it to look like the identity matrix, then if I perform the same row operations on the identity matrix, I can get A inverse. Because then I can also go back the same way. Meaning, if A inverse exists, then I can always make A look like the identity. That's an absolute. It must be row equivalent to the identity. So the way we perform this, it's very clever. I didn't think about it. This is Gauss. He did it a bit before me. I should have misplaced my eraser. Hold on a second. Where did I just... Oh, here. Sorry. It keeps bouncing on the floor. So what we do is we take our original matrix, and I'm going to give you the general because we're going to do this next day, is I take my original matrix, I'm going to call it matrix A. And what we do is we augment it with the identity matrix. So I take my matrix A, which is n by n, and then I slap on an n by n identity matrix. I perform row operations on this until this looks like the identity matrix. Like I just said. Yes.
What did you put some dots or something between the A and the we can't really make that out.
Okay, you're augmenting it. You're taking a matrix and then you're making a bigger matrix out of it by putting the identity. So now you got one really huge matrix here.
Okay, no, is that a symbol or anything, or is that just something you're using to make a reference for us?
Yeah, you guys remember doing that when you were little kids with matrices. I always put little dots before the last column to say that's the augmented. So what I'm going to do is I'm going to do row operations on A, but simultaneously those row operations will be performed on the identity. When I'm all done, I'm going to have a matrix where the left side's the identity, but the right side is actually the inverse. And then I will be able to read it. We're going to do a lot of this next day. So I want to do it with this 2x2 matrix. Okay. I'm going to show you the process. It's actually pretty simple and the results are really powerful. So I start by doing this. A, B, C, D, 1, 0, 0, 1. This is what I mean. I'm augmenting it. I'm putting the identity. Now you don't need to write dotted lines because you know what everything is. I want to do row operations so that the left side looks like the identity at some point. Now, A, B, C, and D are just real numbers. Okay, so I might see fractions and different things like that. No big deal. So the first thing I'm going to do is I'm going to multiply row 1 by 1 over A. By the way, we're assuming A is not 0. We're assuming A inverse exists. We're assuming what we do is possible. By the way, what if A was already 1? Well, great. So now I'd have 1 B over A, 1 over A, 0. Okay. C, D, 0, 1. I didn't really do much. Now I want to take my pivot of 1 and undo the C. And I know I can do that by taking negative C row 1s and adding it to row 2. Now when I do that, I'm going to have 1 and I have 0. C of these would be BC over A, and I'm adding it to D. Yikes. So that's B over A. I'm taking negative C of these and adding it to this. So this would be D minus BC over A. Okay. I'm taking negative C of these and I'm adding it to this. So negative C over A, and then that's 0 and 1. Sorry, this is a little cramped. Okay, just arithmetic. That's all I'm doing. Just simple arithmetic. Now, I need that guy to be a 1, so then I can go back up and do something. So let's take row 2 and multiply row 2 by 1 over D. So my row 1 is 1, B over A.
Professor, for the top row, yeah.
Thank you. That's still a 1 over A. Good. Good catch. Okay, so my top row is not changing. My bottom row, I'm multiplying through by 1 over D. So 0, 1. Negative BC over AD. Yikes. I think that's what I've got. Does that look right? Oh. Hold on a second. My bad. It's not 1 over D. I'm sorry. That right there is what? That's D minus BC over A. So that's actually, we're not doing that yet. Sorry. I need to do the reciprocal of that guy. Oh, but that's so icky. Would I be better off making that into 1 quotient? Because I got to do the reciprocal of it. What do you think? 1 quotient? Anybody? I don't want to take the reciprocal of that.
I agree.
So isn't this the same as AD minus BC all over A? Isn't that what that is? Everybody see that? So that's what's actually sitting here. I need the reciprocal of that. So I need a little more space here. Sorry. Didn't give myself a lot of room there. All right. So we're going to do A over AD minus BC times row 2. So 1 B over A, 1 over A, 0. Now I'll have 0, 1. What is A over AD minus BC times that number? Yikes. Well, let's do it. Right now I have negative C over A. And I'm going to multiply it by A over AD minus BC. That's going to be the new entry here. Oh, that's not that bad. The A's just cancel, don't they? So that number is now going to be negative C over AD minus BC. And in the last position, I'm taking the number 1 and I'm multiplying it by A over AD minus BC. So that's going to be just A over AD minus BC. If I did that correctly. Okay. We have 1 step left. I got to take that 1 and put a 0 here. These numbers look kind of icky, but you know, one good thing, at least they have the same denominator. So the last step, I got to take negative b over a times this and add it to row 1. So negative b over a, row 2 added to row 1. Okay, so now my row 2 is 1, 0, 1. Negative c over ad minus bc, positive a over ad minus bc. Now, a little bit of algebra. I'm going to take negative b over a times this and add it to this. So I'll write it right here. Negative c ad minus bc times negative b over a. And I'm going to add it to 1 over a. That looks like a big yikes, doesn't it? Well, let's see. How about if I write AD minus BC over AD minus BC. Now I have the same denominators. So now I have positive BC plus AD minus BC. Oh, that just leaves me with an AD. So that's AD over A times AD minus BC, and then those A's cancel. It's a big yikes. But that means this position is then D over AD minus BC. Now, to save you a little bit of pain and suffering, I'm going to do the exact same thing here, but negative B over A times this, I'm adding it to 0. Oh, good. So that's just negative B over AD minus BC. And we are now finished. I have my inverse matrix sitting right here. So I'm going to restate this, okay? Let me restate this because I want to make this as readable as possible. All we did was some basic algebra. Now, what looked hideous is I have A, B, C's, and D's. I don't have actual numbers there. But based on what I just said, A inverse, therefore, is D over AD minus BC, negative B over AD minus BC, negative C over AD minus BC, A over AD minus BC. Wow, that's a mouthful. But they all have the exact same denominators. By the way, for any real numbers A, B, C, D, if A inverse exists, your inverse is probably going to be a bunch of fractions. That's okay. They're not complicated fractions. But since they all have the same denominator, let me ask you a simple question. What if I factor that out? What would I be left with? Does everybody agree with that? If I factor out the 1 over AD minus BC, then I'd be left with a matrix. So I just have A's, B's, C's, and D's. And wait a minute. That's the original matrix. Doesn't look like I did a whole lot, does it? It looks like I basically swapped these two and then slapped the negative on these two. Now, that's exactly what we did. There's a shortcut here, in other words. Now, here's the key. The quantity AD minus BC cannot be 0, because if it's 0, I don't have an inverse. So if I give you a 2x2 matrix, as long as this is true, the inverse exists and is incredibly easy to find. I'm showing you a shortcut that only works for 2x2 matrices. Let's do an example. I'm going to show you how ridiculously simple this really is. It's cool. You love this shortcut. Unfortunately, it doesn't apply for 3x3 or 4x4 and so on, but 2x2, it's beautiful. I derived it. I want you to skip to the results every time. I don't ever want you to go through this entire process for the 2x2 because it's unnecessary. So matrix A equals 3, -1, let's say 4, 2. All right. So A inverse equals, well, let's start with this. Said swap those two. Change the sign on those two. We're not done yet. Now I got to put the correct coefficient. The correct coefficient would be, we said AD, that's 6, minus BC. So 6 minus -4 is 10. So my answer would be 2/10, 1/10, -4/10, 3/10. You always multiply it in. So do it in this order and you say, wow, that was really, really simple. 1 over AD minus BC, and then times these guys. Now, I'm pretty sure this is the right answer. I'm pretty sure. Are you guys okay with pretty sure? Or would you like certainty? I think it's obvious.
Nope.
How can I be certain?
Multiply them and see if you get the 0, 1, 1, 0.
Yes, this is an absolute across the board. Never skip this step. You're going to be finding inverses quite often in this course, and you're going to be right the vast majority of the time. But you might not be right 100% of the time because of arithmetic errors. So no matter what you're claiming is your inverse, always check the answer without exception. So I believe it's 2/10, 1/10, -4/10, 3/10. I believe that's the answer. How can I be certain? Let's multiply it out. 6/10 plus 4/10. I'm going to multiply it out right now. And by the way, it doesn't matter what order you multiply because it is the inverse. The one time you can guarantee commutativity of multiplication is if it's an inverse. A times A inverse equals A inverse times A equals the identity matrix if it's the correct inverse. So you don't have to multiply in both directions. So I have 6/10 plus 4/10, that's 10/10. I have 3/10 plus -3/10, that's 0. I have 8/10 plus -8/10, that's 0. I have 4/10 plus 6/10, that's 10/10 or 1. That crowd goes wild, confetti everywhere. It worked, I didn't mess it up. Yeah, this process is supposed to be simple. Finding the inverse of a 2x2 matrix should always be a slam dunk. There's never going to be a time when that's challenging or difficult. The only time the inverse is not going to exist is if that quantity, that AD minus BC, is 0. But for that to be 0, you're going to see can only happen when my rows are actually multiples of each other. What if my original matrix was the 0 matrix? As boring as that is, if my original matrix was the 0 matrix, the 0 matrix doesn't have an inverse. There's no matrix I can multiply the 0 matrix by and get ones. So we realize not all matrices have inverses, but if they have them, we want to be able to find them, and we'd like to find them relatively quickly. Now, we're going to stop there. That's as far as I want to get today.